Alright, so we're going to continue on with organic nomenclature part 2, where we'll talk about some things that are commonly misunderstood or easy mistakes that we can make that we ought to be able to avoid. So let's go ahead and start with something like 2-heptine. Now with 2-heptine, we know that this is telling us the hept tells us there are 7 carbons. The yne tells us there's going to be a triple bond. And the 2 tells us it's going to be on the second carbon, so that triple bond will be on the second carbon. So let's go ahead and start. We'll start with the 7 carbons, 1, 2, 3, 4, 5, 6, 7. And let's go ahead and label them. Call this number 1, number 2, 3, 4, 5, 6, and 7. So it's on the second carbon, telling us that this, if it were here, it would be on the first carbon, so this it's always going to go after the second. 1, 2, 3, it's going to be our triple bond, and the rest we'll fill in with single bonds. This one already has 4, this already has 4 bonds, this one only has 2, so we need 4 bonds, so we're always trying to get 4 bonds on the carbon again. Alright, so that's beautiful and fine and dandy. Now, what if I asked you instead to draw 5-heptine? Well, if we started off in the same way, we'd say, okay, well, there's going to be a triple bond on the 5th carbon, there's going to be 7 carbons, so let's go ahead and draw them. And if we label them 1, 2, 3, 4, 5, 6, 7, we'll draw this triple bond after the 5, right there, fill all the rest in with single bonds. And then if we draw the hydrogens on it, we can go ahead and do that. Actually, let's just do it in an effort to stay consistent. So neither of these need hydrogens. This does. Alright. But these are 3-dimensional molecules. It's not like they always line up. They're 3-dimensional molecules, so you can pick this molecule up. If you were to pick it up and flip it around, what you would notice is that this carbon looks just like that one, and this looks just like that, and that looks just like this. And in fact, when you flip this around, these 2 molecules are actually identical. So why in the world would we have 2 different names? Well, we don't. In fact, 5-heptine doesn't even exist. But if you were to see a molecule that looks just like that, with a carbon, so we got 1, 2, 3, 4, 5, 6, 7. If you were to see a molecule like this, let's just say that the hydrogens are on it already, what you'd want to do is you'd look for the end that has the bond, the double bond, something that's different than a single bond. So I would say it's closer to this end. So we see which carbon is the different bond closest to. So you find which bond, which carbon the different bond is closest to, and you're going to start with that one being 1. So we had a choice. We could either make this a number 1 or this a number 1. This triple bond is closer to this carbon, and therefore we make this one number 1, 2, 3, 4, 5, 6, 7. And of course we're not drawing hydrogens right now. It's easier to see it this way. So 1, 2, 3, 4, 5, 6, 7. Hey, this is 2-heptine when you add the hydrogens. So this molecule doesn't even exist. They're actually interchangeable, so you always want to look for the carbon that's closest to the double or triple bond, and that's going to be your number 1. Some other things you might encounter are cyclo hydrocarbons. So for example, if I said cyclo butane. When you think cyclo, I think you naturally think of a circle of some sort. So let's say I ask you to draw cyclo butane. In order to draw cyclobutane, what you do is you take 4 carbons, because the but tells you that there's 4 carbons, the ane tells you that there's single bond, and the cyclo tells you that they're in a circle. So they all work together like this. And then of course we'd have to label our hydrogens. So hopefully that makes sense. Now, there are also other things that we can encounter, such as dienes and trienes. So let's do an example of that real quick as well. So if you have something like let's say that. So we've got 1, 2, 3, 4, 5, 6 carbons on here, so it's some kind of hex something. It looks like there's going to be enes. There's 2 double bonds here and here. And we could go ahead and fill it in hydrogens. I'm going to ignore, so I'm purposely ignoring H's just because I think it makes it more clear to see. And when you get to organic chemistry, they also will start ignoring hydrogens and use more of a stick model. We'll get there. So right now, looking at this thing, we have 1, 2, 3, 4, 5, 6 carbons. Step number 1 is find which carbon on the end the double bond is closest to. So looking at this, I can see the double bond is closest to this one. So I'm going to call that one 1. This is 2, 3, 4, 5, and 6. And so I've got a double bond on the 1 and also a double bond on the 3. So we know it's some kind of hexene, but there's 2 double bonds. We're going to call it a diene. If there had been 3, we'd call it a triene, 4 a tetraene, etc. So that's a diene because there's 2 double bonds. So here's how we're going to write this. You ask where the double bonds fall. They fall on the 1. They also fall on the 3. We know that this had 1, 2, 3, 4, 5, 6 carbons. So it's a hex. We're going to call it hexadiene. So it's 1, 3 hexadiene. Alright, I think that pretty much covers the majority of things that you'll probably come across. Yeah, have a great day.